Hello everyone, Mr. Waz here, and welcome to another episode of WasleyScience. In today's episode, we are going to be talking about the universe and its stars. So let's get started. Oh boy. In this video, I'm going to be covering 5 next-generation science standards, the disciplinary core ideas, specifically, also known as DCIs. I'm going to be covering all 4 of the universe and its stars DCIs that are for high school earth science, as well as a physical science standard on electromagnetic radiation. These are the topics that we're going to be seeing in this video. We have 7 topics: the Big Bang Theory, stars, the lifespan of stars, electromagnetic spectrum, the Doppler Effect-Redshifting and Blueshifting, as well as Absorption Spectrum and our star. So it's a very ambitious video here. And around on this page, we have some of the big pioneers of modern day astronomy. In the top right, we have Carolyn Porco, and she's very well known. Great writer, and she's doing a TED Talk here on the rings around Saturn that you could click on. On the bottom left, we have Carl Sagan, who wrote the book Cosmos, and he also had a TV series years ago. He actually is the one that inspired Neil deGrasse Tyson when Neil was young into astronomy. And now Neil is very well known. He works at the American Museum of Natural History in the planetarium, and he also is the host of the new version of Cosmos, A Space-Time Odyssey, which you all can watch on Netflix. And in the bottom right, we also have Stephen Hawking, who has been working with astronomy and extraterrestrial life for several years now. So these are people that I wanted you to put a face on, and so when you see them on the news or on TV, you know who they are, and you know that they're all involved with astronomy. So I guess we'll start at, the beginning. Makes kind of sense. And this is called the Big Bang Theory. It's kind of funny because the person that coined that name was somebody that really didn't agree with the idea. It was an astronomer and a talk show host, and he called it the Big Bang Theory, and the name just kind of stuck. So the idea is that 13.77 billion years ago, the universe, on a snap of a finger, just went from being all concentrated in the same exact spot, and the spot that I speak of is like smaller than an atom. So it's the super high density state area, and it just ballooned and expanded very, very quickly. Before this happened, they called the universe a singularity. Since then, the universe has been expanding. There's a lot of interesting stuff about this that we're still just starting to scratch the surface on. But the initial inflation of the universe was greatest at the beginning, and it's been like slowing down a little bit since then. And subatomic particles formed after just a few minutes of the Big Bang. And then after that, larger particles with your protons, neutrons, and electrons formed thousands of years after. Most of the universe is made up of 2 elements. It's our element 1 and our element 2 on the periodic table, which is hydrogen and helium. This is a really cool diagram because what it's showing you is if you look at the shape of the oscillation on the top and bottom of our observable universe, you can see that the oscillation is kind of flattening out throughout time until we end up to today, which that's showing you that expansion is sort of slowing down years after years here. So our first stars didn't really formulate until 13.3 billion years ago, and there is so much about the Big Bang that's like really interesting. If you want to look more into this, there's a book that I've listened to a couple times. It's called Short History of Nearly Everything, and it's by Bill Bryson, and he starts from the beginning of time and he goes all the way to present time, but most of the time he's talking about the formation of stars and the Big Bang Theory. So if you would like a book that is about this stuff that would be really good for you, this is a great book. Did you ever look up at the sky at night and just be like, man, I am so small compared, look at this. I mean, you probably don't get to see the sky like this at night because of light pollution, but it really makes you think about how much is out there. For example, you may look at the sky and see the Big Dipper. That's one that's usually very easy to see at night. You know, just something to think about when it comes to the Big Dipper is you see those stars up there in the sky at night in your viewpoint, but the reality is all those stars are totally different amount of light years away from us. It's so weird to think that, but the lid of the Dipper is 210 light years from Earth, whereas but it looks like to you that they're all the same distance, but they're not. And that's just some perspective I want you all to gain from when you're looking at the stars at night, is they are all different distances from us. Even though they might look like they have the same brightness or they might look like they're the same size, they're all completely different distances from our planet. All right, let's get into stars. So you need to know this. 1 light year is equal to the distance that light travels in 1 year, which that equates to 5.9 trillion miles. Just for some perspective, for you to walk that far, 5.9 trillion miles, you would have had to start before the dinosaurs around and just walking 24/7 till present time to walk 1 light year. That would require a lot of power bars and shoes. I don't know when you would sleep either. Our sun is the one star that's in our solar system. 8 planets revolve around our sun, and then moons revolve around planets, just for some basic vocab here. Then you have galaxies. So many stars will be together in a body called the galaxy, and we are part of what's known as the Milky Way galaxy. Our Milky Way galaxy has about 200 to 400 billion stars. It's a little bit on the average smaller side. And a galaxy can contain millions to billions of stars. It also has dust, interstellar gas, and dark matter. We'll talk a little bit more about dark matter, but what's important is that majority of the stuff in space is actually dark matter, which is kind of weird. It's estimated that there are about 10 trillion galaxies out there, which if we take our galaxy, the Milky Way, and we times that by 10 trillion, it comes out to that there are about 1 septillion stars in the universe. That's how many stars are out there. Now, when you look up there at night, you see about 9,000 of that 1 septillion. So that's just some perspective, is when you're looking out there, you're like, oh wow, look at all the stars. You're only seeing 9,000 of them. There's 1 septillion of them. Now, Andromeda is the closest galaxy that is to us. It's 2.5 million years away, which means that when we're looking at it, we're looking at how it's doing 2.5 million years ago. And if there's one of those planets and surrounding one of those trillion stars that it has that's looking at us, it's looking at us 2.5 million years ago. Andromeda is much bigger than the Milky Way. It's got a lot more stars and it's expanding. And in 4.5 billion years, our galaxies are going to collide with each other. But we're going to be dealing with other problems like our star, the sun, expanding. If you'd like to watch a quick video to get a perspective of how many stars are out there, you can click on the bottom right here. It's a great short video. Let's get into the life cycle of stars. Now, all stars start out, no matter what pathway they go, as a stellar nebula. And a nebula is a massive amount of dust, hydrogen, and helium gas. It's in its plasma state. The nebula is very small. It would be like the size of Earth and weigh a few kilograms. It's very not dense at all. This is how stars are born. What happens is that the dust and the elements will clump together and become denser and denser. Now, the next path that we're going to talk about is the main sequence, which is this top path that you see on the diagram. So we're going to talk about the main sequence stars. Then we're going to go and talk about the other sequence that you can see. 90% of stars go through this main sequence. When you have your typical star like ours, what's happening inside is that hydrogen is fusing together and becoming helium in its core. They can vary in size as well as their brightness. And the big thing to understand here is that gravity is pulling the star inward, and the pressure from the fusion is pulling the star outward. And what happens is that inward and outward push and pull are sort of equal, so the star overall for a very long time maintains its size. But eventually the star becomes a red giant. And so you can see this diagram in the bottom right over here. The sun, our sun, is so small compared to what a red giant is. A red giant is 100 times larger than your typical sequence stars. The reason why this happened is the star consumed its supply of hydrogen, and so it can no longer generate that outward pressure to counteract with the inward pressure, and thus the star just balloons, it expands. What really is cool is that the helium in a red giant's core will begin fusing together and become larger elements than helium, like lithium and carbon. Eventually, the red giant will expand so much that it will become a planetary nebula. And so it's not really a star, it kind of exploded. And it ejected all this ionized gas as well as all those interesting elements that were going on inside the star when it was fusing itself. And those elements can get brought to distant galaxies. That's why on Earth we have all the elements that we have here. They came from planetary nebula as well as supernovas, which we'll talk about in just a little bit. And so these stars they expel their elements that fuse inside of them. Now eventually a planetary nebula can become a white dwarf star. Now there's no more fusion that's occurring, so the star collapses inward under its own gravity. And the star will only be like the size of what Earth is. It's very small. It'll last for hundreds of billions of years and just be cooling down. It's not very bright, but it still obtains its high temperature. You could also have a red dwarf star. This is the most common star that's in the universe. It has very low mass, it has low temperature, and low brightness, so everything's dim. What's interesting about this star is this star can greatly outlive a white dwarf star because it'll keep its hydrogen fuel for longer, and it can estimate to last for trillions of years. But it's not really big enough or bright enough or hot enough to sustain life on the planets that are surrounding it. Now we're going to start talking about this other path here. And so what happens in this other path here is you get things called blue giant stars. You can have blue giant stars as well as blue supergiants. You can also have red supergiants. So this pathway is like a more intense pathway, but a much shorter lived pathway. So blue stars are large and compact. They burn through their hydrogen very quickly, and their temperature and their luminosity is extremely high. They're the highest of those. They're short-lived. They live for 10,000 to 100,000 years, which is like nothing in Star World. And they eventually explode, and these red supergiants or blue supergiants will become a supernova. You probably heard of this word. It's when a star explodes. They're difficult to see from Earth because the Milky Way has dust all around that sort of obstructs our view of seeing these supernovas. But they're a little like planetary nebula in the sense that they can distribute elements to faraway galaxies. Now, what's really exciting is that these supergiants, because they're so much more massive, they can make even heavier elements on the periodic table. And they can go all the way to iron. So that's how we have iron on our planet, is because of supernovas of stars that died. They exploded and made their way to other solar systems and galaxies so far away, including our own. Now, eventually, the supernova can become a black hole. Black holes are really weird. They are this region with such powerful gravitational field that light can't even escape them. And they can be as small as like one atom, but have the mass of a huge mountain. And when we look at space, we don't see them, but we see the result of around them. And that's how we're able to figure out these black holes. Is like we don't actually see a black hole. We see a strong gravitational field all heading to one specific spot. If you need a quick review on the life of stars, feel free to click on this video up here in the top right, and it will break down everything I just talked about with some great visuals. This diagram shows the relationship between color and temperature of a star. The lowest temperature stars are the red ones, and the highest temperature stars are the blue ones. It goes from red to yellow to white to blue. And you can just see the difference in temperature. We're talking about a difference in like 20,000 Kelvin. That's a huge amount. There is a very important misconception that this diagram directs that you need to realize. When you think hot, you think red. When you think cold, you think blue. It is not that way when it comes to stars. It is the opposite. When you think blue, it's hot. When it's red, it's cold or colder. I mean, 3,500 Kelvin is really hot still, but nowhere near as hot as a blue star. Think about it this way. When you initially start a fire, it usually shows as a blue flame, and as a fire dies, it becomes red. So it's the same kind of thing that's going on here. All right, just an FYI. If I was to make this video into a part 1 or part 2, this is where I would break it in half. So if you're watching this right now and you've got to this point, I would honestly take a break. This was a lot of material. Take a break and then watch this next part later on. Let's get into an HR diagram. Now that we've been able to separate these stars and categorize them, a Hertz-Russell diagram can make a lot more sense. So what the purpose of this diagram is very important. It classifies stars according to their luminosity, their type, their color, their temperature, and even their evolutionary stage. So it's a way of saying where all the stars go in comparison to one another. And stars in the stable hydrogen burning lie along what's called the main sequence to their masses. And so what you see here, if we make this image larger, we can see that when you move from the bottom here to the top, or the top to the bottom, doesn't really matter, these are the main sequence stars. What's interesting here, so our star is around here in the main sequence, but it shows that you got the red supergiants, you got the red giants, you got the blue giants, and then you got the white dwarfs over here. And so if you look at the y-axis, you can see that the y-axis is luminosity. Luminosity means brightness. So the higher you are on the y-axis, the brighter you are as a star. If you look at the x-axis, it is based on temperature. So the more closer you are to the left, the hotter you are as a star. And if you move to the right, this is a colder star. So what we can clearly see here on this HR diagram is that red stars are cold, and then it goes to orange, and then yellow, and then kind of white, and then blue stars are the hottest. We can also see here that white dwarfs are very hot, but they are very dim. You can also see that blue stars are very bright and very hot. And then red stars, like red supergiants, can be very bright, but they still don't retain a high temperature. And in the middle, you got the regular old yellowish stars. So they're kind of bright, kind of hot. An HR diagram can really be helpful for classifying stars. To help us understand astronomy, we really need to look at the electromagnetic spectrum. Electromagnetic energy, energy that moves through empty space, can be classified in wavelength. So this little rainbow part here you see in the band is the part of our universe that we actually see with our eyes. We call this the visible light. And you can see that if you look to the right, you can see your sort of rainbow effect here. So you got red, orange, yellow, green, blue, indigo, violet. To the left of violet is something called ultraviolet rays, which you may have heard of. And to the right of red, you got infrared waves. The electromagnetic spectrum makes up all the kinds of energy that moves through empty space. When you look at the right, radio waves and broadcast band waves are the longest wavelengths. This means that they can travel and their energy is not very concentrated, so they're not very harmful. And then eventually you get radar and microwaves and infrared waves. And when you're moving from these long waves towards the other side, then you get onto shorter waves. And these rays, the short wavelengths, are much more harmful to us. And the reason is because when the wavelengths become shorter, you can see that they become more concentrated. Those sort of waves become more closer together. And when the waves become closer together, that means the energy is more concentrated together. And when the energy is more concentrated together, it can be more harmful to you. That's why you don't want to get hit with gamma rays and X-rays. And radio waves go through you like all the time, and you don't notice, it doesn't bother you, it doesn't do anything to you. Another really interesting thing about the electromagnetic spectrum is yes, this is the light that we can see, but there's parts of the electromagnetic spectrum that we don't see that other animals can see. So for example, if you take the snake can see infrared waves that we can't see. So it uses that to detect heat, because if it can detect something that's hot, that must mean it's alive, and so it uses that to hunt. And then you got hummingbirds. Hummingbirds can actually see some ultraviolet rays, and they use that to detect different nectar that's in flowers. So these flowers broadcast those colors that we don't see, but the hummingbird does. Now that's kind of as far as we know what animals can go in terms of seeing on the electromagnetic spectrum. But it's a way to basically quantify color, but also quantify all the other types of ways that energy can travel through empty space. Let's take what we learned from the electromagnetic spectrum and apply it to the Doppler effect. Spectroscopy is the study of the interaction between matter and the electromagnetic radiation. And the Doppler effect has a lot to do with that. You probably have heard of the Doppler effect before. When a siren is heading toward you, it has higher frequency. And then when it heads away from you, it has lower frequency. What's happening there, if we look at this diagram on the bottom right, you can see that as the siren is heading toward you, that the waves are more concentrated. So when it's more concentrated, you have a higher frequency. So the siren sounds higher. When it is leaving from away from you, the lines here, the waves are farther apart, so that creates a low frequency, so it sounds lower pitched. Now here's where it gets really interesting. We can point a telescope at a specific star and take what's called a rest frame. So when we take this frame, it will show us the specific colors that are coming back to us, and it will reveal to us a sort of electromagnetic identity. When we take a frame moments later from that rest frame, we can see that it has either redshifted or blueshifted. Redshifted means that the initial fingerprint has moved to the right of the spectrum. And what that shows is that the thing that you're looking up with your telescope, which is probably a star, right, is receding from you because it's getting a lower frequency. It's heading to the right of the electromagnetic spectrum, which would indicate lower frequency or longer wavelengths. Now, if you look at it on the sky and you see that it's called blue shifting, that would mean that your sort of electromagnetic fingerprint is heading towards you because the bands on your fingerprint are becoming high frequency because they're heading more towards blue. So blue shifting means that the object in the sky is heading towards you. Red shifting means that the object, which is most likely a star, is heading away from you. An easy way to remember this is the taillights of a car are often red. And when are you looking at red taillights? Well, when the car's driving away from you. And when do you see blue headlights? I mean, some cars have blue LED lights. That would indicate that the car is heading towards you. And what this boils down to is when it comes to spectroscopy and we look with a telescope into the universe, we see that almost all the stars are heading away from us. In other words, they're red shifting, which means that the universe is expanding at every moment. That means that the universe is becoming larger every moment. Every moment, every second becomes another second that's even harder to get out to other galaxies. Kind of makes it a little depressing and show how alone we truly are. This diagram helps review what we were just talking about here. So you can see the sun in sort of the middle there. It's a little to the right because when it's blue shifting, you see the eye is like where you're standing. When it's blue shifting, the bands are closer together, which would indicate that the object is coming closer towards you. On the left side, you can see red shifting happening because the bands, the wavelengths are longer, therefore the object is moving away from you. And I want to point out that the whole red shifting and blue shifting can be confusing because we were just before talking about red stars and blue stars, and now we're talking about red shifting and blue shifting. And a star that is red doesn't mean it's moving away from us, and a star that is blue doesn't mean that it's moving towards us. That has nothing to do with it. This is a totally different thing. So do not get confused with red shifting, blue shifting, and red stars, blue stars. You can have most stars, like I said before, are moving away from us. So there are plenty of blue stars that are moving away from us. Absorption spectroscopy measures the absorption of radiation as a function of frequency or wavelength due to its interaction with a sample. In other words, it uses color to detect what elements are present. Each element on the periodic table has a distinct pattern on the electromagnetic spectrum. So if we look at this diagram here, so here's basically what happens. We take some sort of hot source and we run it through a type of cloud. In this case, this is a cloud of hydrogen, but we can also do a helium in its gas form. We could also do neon. We can do all the different elements one at a time. We run the hot source through the cloud, and then we have a little slit. And then after the slit, we have a prism. You probably have heard of a prism before, but the prism sort of refracts the light. What happens is the gas of the element absorbed certain colors, certain wavelengths on the spectrum. And so those very specific colors that we wouldn't see with our naked eye become missing. And it makes these sort of black bands on the spectrum. And each element has a certain code. It's like a code, like a fingerprint, just like before. Every single element has a different one. So in this situation, it's showing hydrogen here has 1, 2, 3, 4 bands in the electromagnetic spectrum that the gas absorbed. Like I said before, each element absorbs very specific and different parts of the electromagnetic spectrum. What it allows us to do with our telescopes is we can point it at the universe, at different stars, at different planets, and it can do so much without us having to actually physically visit that planet or star. We can figure out the composition of an atmosphere to another planet. We can study the elements that are expelled from a supernova or a planetary nebula. We can categorize stars by the amount of hydrogen that they have. And also, here's the big one, we can measure temperature, pressure, and even mass of a planet or star light years away with this skill here. It is so useful. Let's take a look at some examples. So hydrogen has this basic code. When you run a hot source through a hydrogen gas, this is the colors of the spectrum that get absorbed. And you can see by these 5 elements here that each one has a different amount of colors that gets absorbed. So we can use this and figure out what types of elements are out there in the universe. Very important and crucial technique that we use. We are going to finish this video by talking about our star, the Sun. Its nickname is actually Sol, S-O-L. Most stars in the universe are red dwarfs, which actually puts our star in the top 10% of stars in the universe. Our star is 1.4 million kilometers in diameter. That's 100 times the diameter of Earth. And that also means that 1 million Earths could fit inside of the Sun. The pressure in the core of the Sun is 260 billion times Earth's atmospheric pressure. That's nuts. It's also 15 million degrees Celsius. It's so hot that hydrogen becomes ionized and fused together into helium. So 1 + 1 = 2, right? Element 1 + element 1 = element 2, helium. The nuclear energy, this fusion, then releases outward. This has to do with Einstein's E energy = mc², mass times speed of light squared. This massive amount of pressure ends up releasing energy. The atoms that make up the Sun have their electrons stripped from them. So the Sun isn't even really technically a big ball of gas. It's a big ball of plasma. Plasma is a state of matter that is beyond gas. And what ends up happening is that the Sun's surface is so unpredictable and hot and crazy that there's solar magnetic fields that exist. And from this, you can have solar flares and coronal mass ejections, which are also known as CMEs. And these can emit from the Sun and do so much damage. They're basically these really hot amount of rays that come and can hit the Earth. They've hit the Earth in the past. If they hit the Earth right now, they could incinerate some of our satellites and throw us to our knees because of our dependency of technology. So the Sun is very powerful and it can do a lot of damage. We need to respect its power, even though it's so far away. If we look on the bottom of this diagram, we can see the life cycle of the Sun. So right now the Sun is about 4.5 billion years. And what's going to eventually happen is that the Sun's going to warm. That's not what's happening right now. That's not what climate change is. This is stuff that takes billions of years, people. So eventually the Sun is going to become a red giant. And when that happens, it's going to consume the planets, including ours. So either the Andromeda galaxy will consume us or our own Sun will consume us. But, you know, this planet has about a couple billion years left of sustainable life. And after that, it'll become a planetary nebula and then a white dwarf. Alright guys, thank you so much for watching. I have lots of videos here. There's so much in astronomy to just really sink your teeth into. On the top left here, we got a Stephen Hawking documentary. In the middle, you can see a really cool star size comparison. So it shows how big planets and suns are. All the way to the right, you can learn more about dark matter. And on the bottom here is a YouTube channel known as Crash Course. They have some great astronomy videos that are all about 10 minutes long. There's about 48 or so of them. We have one on the Big Bang, we have one on stars, and we have one on light. So feel free to click on any of these videos. So thank you so much and take care.